Hi, this is the first lesson on parametric equations. So up to now you have worked solely in Cartesian equation form. So a Cartesian equation is one that just involves an x and a y, so where the relationship between x and y is given directly. So for example, you might have y equals 2x plus 3. That is a Cartesian equation where y is given in terms of x. Okay, so that is the Cartesian equation for a straight line. You could have x squared plus y squared equals 4. Okay, this time y is not in terms of x, so it's not explicitly written in terms of x, but that is a Cartesian equation because that is a direct relationship between the x and y coordinate, and that is for a circle centre origin radius 2. Okay, sometimes it's easier to work with graphs if they are given in terms of parametric equations. The word parametric comes from the word parameter, and a parameter just means another letter. So if you look here, if I can enlarge that, okay, this complex looking curve called a butterfly curve, okay, has been given as parametric equations. Okay, the parameter in this case is the t. So you can see instead of one equation that just involves x and y, we've now got two separate equations. Both of them are in terms of t. So the t is the parameter. And these two complex looking parametric equations together produce that beautiful looking butterfly curve. Okay, so the t is the parameter, and together they are a pair of parametric equations. Now you're not going to be dealing with anything as complex as that, but you do need to be able to work with parametric equations. And the reason why we do work with parametric equations, one, because they produce much more complex looking graphs, as you can see with that butterfly curve. There's some more examples on the next slide. As you can see, these are actually moving. So we have the thing on the left, which are called Lissajous curves, marking it out. So it's called tracing it out. So it's tracing out the curve. So as t changes, the curve gets traced out. We also have the hypotrichoids. Again, much more complex graphs than you will be looking at in the syllabus, in the A-level syllabus, something you might look at in your degree. And then the one on the right, that's in 3 dimensions. There are 3 parametric equations where the parameter is t, and that's actually tracing out what we call the helix. Okay, so each of those, that pair there, that is a pair of parametric equations. We've got 3 parametric equations for the helix. Okay, so they come as pairs or threes. Now you're going to be working in pairs. Okay, these are the things that you're going to have to do. So we need to be able to plot and sketch curves given as parametric equations. And you're going to have to be able to convert from the parametric equation to the Cartesian equation. We're going to have to use parametric equations to solve geometric problems, so work out where they're crossing the axes, work out where 2 parametric equations are intersecting with each other. We're also going to be able to have to differentiate parametric equations, and we're also going to have to integrate parametric equations. Okay. So here's just a little explanation now about why we use them. So it says graphs and their associated problems involving plotting, gradients, areas, tangents and normals are sometimes very complex if the graph is in Cartesian form, i.e. in terms of x and y. Okay, these problems are often made easier by considering the graphs in parametric form, where x and y are separately written in terms of another parameter. So we usually use the letter t or sometimes theta. Parametric equations, as I've shown you, are used for much more complex graphs. We've used them in kinematics when we've been looking at projectiles. Okay, so the first thing we're going to do is we are going to use the parameter to actually plot the graph. So what we're going to do is I want you to understand what the parameter is doing and how it creates the graph. Once you've sort of grasped what's going on by plotting the graphs, it'll be much easier for you to be able to solve problems involving these parameters. Okay, so we're going to plot two graphs. So you're going to need a pencil, your calculator. Okay, it says a curve is given by the parametric equations x equals t squared and y equals t cubed over 5. Complete the table and draw a graph of the curve for t is greater than or equal to -4 and t is less than or equal to 4. Okay, so we've got a pair of parametric equations, so they come together. So all that t is acting like is a bit like a go-between. So for different values of t, we are going to produce values of x and values of y, which we are then going to plot on our graph. Okay, now this range of values here is called the domain of the parameter, and that's dictating what values of x and what values of y we can use for our graph. Okay, so we've got a table of values. So t is going from -4 and then it's increasing by 1 each time until it gets to 4. Okay, we can work out the x coordinates by simply substituting our values for t into the first parametric equation. So we know that x equals t squared. So if t is -4, then x will just be -4 squared, which is 16. When t is -3, then x will be -3 squared, which is 9. When t is -2, x will be -2 squared, which is 4. When t is -1, x is -1 squared. When t is 0, x is 0 squared. When t is 1, x is 1 squared. When t is 2, x is 2 squared. When t is 3, x is 3 squared. When t is 4, x is 4 squared. Okay, so those those t values from -4 to 4 have produced our x coordinates, which go from 0 up to 16. Now we can work out our y coordinates by substituting the t values into our y parametric equation. So when t is -4, y is -4 cubed divided by 5, which is -12.8. When t is -3, y is -3 cubed, which is -27, divided by 5, which is -5.4. When t is -2, y is -2 cubed, which is -8, divided by 5 is -1.6. When t is -1, y is -1 cubed, which is -1, divided by 5, which is -0.2. When t is 0, y is 0. When t is 1 cubed is 1 over 5, that's 0.2. When t is 2, 2 cubed is 8, divided by 5 is 1.6. When t is 3, 3 cubed is 27, divided by 5 is 5.4. And when t is 4, 4 cubed is 64, divided by 5 is 12.8. So we've substituted t from -4 to 4 into each parametric equation, and that has produced a set of x values and a set of y values. Okay, so all we need to do now is plot those two for x against y. So we're not actually plotting the t values, we've just used the t values to work out our x and y values. And then we're going to plot that on our x and y axis. So here's x, here's y. So for x, the smallest value is 0 and it's going up to 16. So x is 0. I'm just going to zoom in. So I'm just going to go up in 2s. 2, 4, 6. No, I'm not. Is it going to fit? 2, 4, 6, 8. So I'm going to have to go up in 2s that way. 2, 4, 6, 8, 10, 12, 14, 16. And then I need to go from -12.8 to 12.8. So 2, 4, 6, 8, 10, 12, 14. And then -2, -4, -6, -8, -10, -12, -14. Okay, so I'm going to just start from the left. So where t is -4, we've got x is 16 and y is -12.8. So x is 16, y is -12.8. So that's about there. Okay, so I'm just going to point out that that's our start point for reasons I'll explain in a minute. When t is -3, we've got x is 9 and y is -5.4. So x is 9, y is -5.4. About there. Then when x is 4, y is -1.6. When x is 1, y is -0.2. Then it goes to the origin. When x is 1, y is 0.2. When x is 4, y is 1.6. When x is 9, y is 5.4. When x is 16, y is 12.8. Okay, so it starts here at 16 minus 12.8, and then the graph, as t increases by 1, the graph goes to the origin and then goes up there like that. Okay, now I've drawn it that way for a purpose. Okay, the direction that it's being plotted in as t increases is called the trace. So I'm just going to put some little arrows on. You don't need to necessarily, but that is called the trace. And it's important that you understand the direction that the graph is being traced out in as t increases. Okay, now the domain of the graph that we have produced, the domain, the possible x values, you can see goes from 0 up to 16. So x is greater than or equal to 0 up to less than or equal to 16. The range of that graph, so f of x, well, you can see the lowest value is minus 12.8. and the greatest value is 12.8. Okay, now we could have worked that out had we not drawn that graph. So if you just had the parametric equations, so if we just had that information and that information, you may be expected to be able to work out what the domain and the range are without drawing it. Now we can do that by considering what t is against x and what t is against y. So I've just at the side here, I've got two little tiny graphs or tiny boxes. Okay, if I consider what x equals t squared look like, okay, so if I plot x equals t squared for t against x, that's a bit like plotting y equals x squared for x against y. So that would look like, if I just draw that in, that would look like that. And that would go from -4 to 4. So where t is between -4 and 4, x is between 0 and 16. The range of this little graph here is from 0 to 16. So this here relates to the range of the x parametric equation. So the domain of the Cartesian graph, the domain of the graph that it's been produced, is actually the range of this first Cartesian equation. Now if I consider y equals t cubed over 5, so if you think about what y equals x cubed over 5 would look like, that would look like that. Because it's just a stretch of x cubed graph. Okay, so for -4 to 4, so that is the domain of the parameter -4 to 4, the y value is going from -12.8 to 12.8. So this here is the range of the y parametric equation. So we can work out the domain of the actual graph for x against y by considering the range of the x parametric equation. And if we want to know the range of the actual graph, then we need to consider the range of the y parametric equation. Okay, let's have a look at another one and we can put that into practice. So we have got a curve is given by parametric equations. X equals 2 sine t and y equals cos t. Complete the table and draw a graph of the curve for t between 0 to 2 pi. So again, this is our domain of the parameter. So we have t values going from 0 up to 2 pi, and you can see it's going up in pi on 6s. So we're in radians. Okay, part of the table's been drawn in. So let's fill in the table. Okay, so when t is 0, x is 2 sine 0, which is 0. When t is pi on 6, x is 2 sine pi on 6. Well, sine pi on 6 is a half, so 2 sine a half, 2 times a half is 1. Pi on 3 is done. When t is pi on 2, 2 sine pi on 2 will be 2, because sine pi on 2 is 1. That one's done for us. When x is when t is 5 pi on 6, x is 2 lots of sine 5 pi on 6, which is 1. When t is pi, 2 sine pi will be 0. That one's done for us. 4 pi on 3, so 2 sine 4 pi on 3 is negative 1.73. That one's done for us. When t is 5 pi on 3, x is negative 1.73. And when x is 11 pi on 6, when t is 11 pi on 6, x is minus 1. Now we can work out the y values by substituting the t values into cos t. So when t is 0, y is cos of 0, which is 1. That one's done for us. When t is pi on 3, y is 0.5. When t is pi on 2, cos pi on 2 is 0. When t is 2 pi on 3, cos of that is negative 0.5. When t is 5 pi on 6, cos of 5 pi on 6 is negative 0.87. That one's done. When t is 7 pi on 6, that's negative 0.87. That one's done. When t is 3 pi on 2, y is 0. When t is 11 pi on 6, y is 0.87. And when t is 2 pi, y equals cos of 2 pi, which is 1. Okay, so again, we're going to plot x against y. So you can see x is going from minus 2 to 2, and y is going from minus 1 to 1. So if I say that's 1, oops. Just move that by accident. Better. So that's 1, that's 2, that's 1, 2, 1, 2, negative, that's 0. Okay, so the first point when t is 0 is the point 0, 1. Okay, so that is my start point. Then when x is 1, y is 0.87, which is about there. When x is 1.73, y is 0.5. Then we've got when x is 2, y is 0. When x is 1.73, y is negative 0.5. Then 1. Then 0 minus 1. So you can see it's tracing round in a clockwise direction. So that's going to go there. And then that'll go there. Whoops, there. Then there. Then there. Then there. Like that. Okay, so it's going round in a clockwise direction. You can see, hopefully, I've drawn it a bit wonky. So that was the trace. And it has produced an ellipse. So we've traced it round in a clockwise direction. It started and finished at the same point, and that's because it went from 0 to 2 pi. So it did one full loop. Had that gone from 0 to pi for t, then it would have started there and finished here and would have just done half a loop. But because it went from 0 to 2 pi, it would traced out the whole loop. Okay, now again, we can consider the domain and the range of the original graph. So the domain is a set of possible x values. So that's -2 to 2. And the range, which is the set of possible y values, is -1 to 1. And again, we can consider the separate parametric equations. So if you just think of x equals 2 sine t, if I draw x equals 2 sine t on my little axes, that would look like that, where that's at 2, and that's at -2, and that's 0, and that's 2 pi. So for 0 to 2 pi, for t, the x values range is from -2 to 2. So this domain here, we can figure out, had we not even drawn the graph, by just considering what the range of that first parametric equation is. And it's going from -2 to 2 because there's a vertical stretch. Now if I consider what y equals cos t looks like, well, that just looks like that. From 1 to -1 and 0 to 2 pi. So t is going from 0 to 2 pi as y goes from -1 to 1. So again, this we could figure out by considering the range of the y parametric equation. Okay, so here it says, so this is the bit that I've just been getting at. For parametric equations, x equals pt and y equals qt, with Cartesian equation, y equals f of x, the domain of the graph that it produces is the range of the x parametric, and the range of the graph that it produces is the range of the y parametric. Okay, so if we have a question where we don't have the graph, but we do have the parametric equations and the domain of the parameter, the values for t, we can work out the domain and the range.